Okay, good morning. So today I'm going to finish up the chapter on mass storage, and this is where we left off last time. We were starting to talk about RAID structure. And RAID initially stood for Redundant Array of Inexpensive Disks. That was at the time when I first learned about it. And I took the class at Berkeley, and the professor was the inventor of RAID, Dave Patterson. And that was actually a new concept at the time. And now you see RAID a lot. Even at home, you can have your own RAID. And that was at the time when these hard drives were starting to become made more for personal computers. And of course, they were made for workstations as well. Over time, the inexpensive part got replaced with independent disks. It really just depends on what your emphasis might be. So there's two possible ways to look at this. One is for redundancy reason, because disks, as you know, fail over time, and not all at once. Sometimes the entire disk could fail. Other times, it's one sector at a time. And so having redundancy helps, because you have disks that are entirely different unit. So if, say, the controller on one fails, chances are it's not going to affect the controller on another one. So that's where independence or independent disks come from. That's really the consideration for reliability. But these being architecture people, they're used to the idea of parallelism, especially pipeline parallelism. That's what RISC is, a lot of what RISC is about, is you can pipeline the access, and same thing with the memory. They do memory banking so that when you start accessing, you actually you issue these access commands to different memory banks. So that way, hopefully you don't have to wait for one transaction to complete before you start the next one. You pipeline them. And also you can spread data over across multiple disks. That's where you also get parallelism. So striping is that concept. Striping is split your data across multiple parallel disks to get data parallelism. Okay, that hopefully improves performance. But again, this, strictly speaking, is supposed to be covered in an architecture course. This textbook chooses to cover it in an OS course. So, okay, I'll tell you about this. So RAID has a couple considerations. One is the mean time to failure of these disks. And usually these are on the order of 10 or more years. But they're usually rated in terms of hours, or 100,000 100,000 hours of actual access. Of course, no, there are a lot more than 100,000 hours in 10 or 11 years. But that's really means average. So what does that mean? That means you're averaging over all the disks, at least from what they test. So does that mean all disks will fail at like 11.4 years? Not really. Some will fail earlier, some will fail later. Some might never fail, right? I mean, that's unlikely, but from what they can test. So that does mean some disks will fail much earlier. So in fact, if you work this out, 1 out of 100 disks will fail in a little over a month, in 41 days. Okay, and that's why there's warranty on these. And so chances are, if it fails, it's likely to fail within like a couple months. And if after a couple months it hasn't failed, then chances are it's much closer to the average, or you can expect it to last for about 10 years or so. And so what can you do with the disk that can fail? Of course, obvious thing to do is you keep another copy exactly like it, right? And you probably do that. So if you have important data you can't afford to lose, what do? You make a copy of it, right? So from time to time you mirror it, or so that is one thing you can do. But mirroring may be done either automatically or you set up a script, but that disk has to be also connected. And so one thing what RAID can do is it does the mirroring automatically for you. Okay, that way you don't have to worry about, oh, hey, did I forget to mirror my disk or incremental backup of my disk to another disk, right? So mirroring means making an exact copy. Okay? Every time you write, you do want the write to also show up on the mirror disk. Now you can do mirroring simultaneously. That is one command and then issue to both drives. Or you could do it kind of asynchronously. That is, you set up like once every day to check what has been written, and you could also do it on demand. So one way or another, you kind of want this to be able to automate itself, right? But then you do have to anticipate the situation where, what if a disk fails? It could be either the original disk, or it could be your mirror disk, right? You say, well, let me mirror onto multiple disks then. Well, yes, you could do that, but then that starts to become more problem. Mirroring, yes, it is one straightforward way to do it, but there are probably better way to do it because it does tie up an entire disk just for the exact copy. And so that means you either easily double, triple, quadruple the amount of hardware on storage required for the actual data you have to store. And data centers and all these others, they don't do exact mirroring like this. They do something a little smarter. Now, mean time to repair is the average time it takes to first discover if a disk has failed and to replace. Right? So this is not related to mean time to failure. The next metric, though, the mean time to data loss, that is actually related to both. But then mean time to repair is, think of it as you're the system administrator, or you administer your own computer. And maybe as part of mirroring, it reports back, hey, one of the disks failed. Well, it may have failed earlier, you just haven't discovered it, right? And so the average time it takes to discover it, maybe it doesn't send notification, maybe it doesn't show this unless you are actually doing the backup or mirroring. Then once you discover it, what do? Well, you attempt repair, right? And not only that, you may have to do some restore as well. So the repair would be like you have a tool that does a repair because some blocks may have, not have been linked correctly. Maybe there's some bit error here and there. It could check and maybe it could repair as well, but it usually would tell you if it's something more serious. And there's times when they can't repair, but are you done there? No, there's time you can actually recover, right? Based on modification date and all that, you could actually say, well, I lost it on this one, but since that was from a couple of days ago, I do have a mirror copy still there. So it takes time to go through and compare possibly to see, well, can I recover this from my mirror disk, right? So one or the other. And then, so that restoring it requires data structures of file blocks to be relinked and copied over and set the modification date and all that. And if you can do that successfully, then great, then you have successfully done that. Otherwise, what do you have to do? You have to bring out a spare disk, right? So that means one is not rescuable, replace it, put in a new one, but the new one doesn't have your data, so it takes time to copy from that your good disk over to your fresh spare, right? And guess what? During this copying or restoring, your other disk could fail too, right? So I mean, the chances of that is unlikely to be very high, but it's not a zero probability, right? So you have to work out the average of the math, and so so this is with a big assumption of these disks fail independently, but do they? So I'll talk about that in a little bit. The mean time to data loss is when that bad situation happens. You discover one that's failed. You're trying to build up another mirror or repair this one. If it doesn't work, build up another mirror. just so that you can do your best to keep all the data you have. But then your only copy now has failed, and then that you just lost all your data. Okay, that's the mean time to data loss. And so what's mean time to data loss? Well, so what you do then is you take mean time to failure, and if there's two of them, square them, and then divide it by mean time to repair. And if there's two, right? Because your only copy, that you could still repair it if you want, but then if you couldn't repair it in time and the other one still fails, then yes, then you actually have lost data. So 100,000 hours squared divided by 2 times the mean time to repair, that works out to be 57,000 years. That's a long time. But is that really the case? In practice, what's the case? So that's what I did exactly. I bought 2 identical disks, and I kept them mirrored. And I was hoping that I wouldn't be so unlucky that both would fail. But guess what? They failed within a few hours of each other. They're from the same batch. I guess they had similar characteristics. So if they were truly independent, then you're likely to have that 57,000 years of mean time to data loss. But in practice, no. They were disks from the same batch, and I suspect they experience a similar characteristics. And whether it's the controller or it's the way the disks are manufactured, I don't know. So if you have to do mirroring, I really recommend getting them from different companies, different manufacturers from different times. That increases that really reduces your odds of them failing together. Okay, another may be the kind of assumption you make. So for example, they may be plugged into exactly the same power supply or same power strip. And sometimes these failures are due to surges. Right? Maybe there is a sudden surge in your power line, right? Maybe your neighbor sometimes just shorted everything out, and that causes a dip. Or maybe there's and then there's a spike in the power line. Well, that may affect both your disks, your mirror and original, and then they might not fail right away, but that causes serious damage to the power supply. So it's failing quickly, okay? And so that may be a case where, that might have been what happened to my own case. But yeah, the same brand, exact model, same batch, but they failed within a few hours of each other. So yeah, and also as these disks age over time, the likelihood of them both failing also increase. So I would recommend, if you have to do mirroring, get them from not only different manufacturers, but from different ages too. So after some time, put in a new disk that is similar capacity, and then do your mirroring that way. Okay. So yeah, if you have data you can't afford to lose, to try to diversify your disks in terms of the brands, the model, the age, and so forth. Okay. Yeah, there are a few potential solutions, but they're not exactly solutions. So you could do some non-volatile memory, some SSD or other structure as kind of a cache, so that you accumulate these writes. And just in case of the true disk failure, as long as you have another way of accessing the remaining data, you can get most of it back, plus the latest copy on the non-volatile storage. Okay, so in addition to reliability, redundancy, RAID primary motivation was to improve the performance by data striping. Because these people, I mean, if you think back, these were computer architects. They did RISC, but part of RISC architecture was the concept of caching as well. I mean, caching is not limited to RISC, but RISC relies a lot more on the caches. Why? Because their instructions are bigger, so they need even more need of cache to be able to access instructions quickly, data as well. And also, disk can be pipelined, and that means the processor gap with the memory speed is bigger, and that's why cache is even more important. Now, they do worry about this speed gap between different levels of memory hierarchy. Processor is very fast, register very fast, cache a little slower but closer to processors. Main memory much slower, disk even slower, much slower, right? So they are thinking, how can we increase the performance of the disk? Well, put in more disks, right? A lot like how they solved the memory problem by memory banking. So data striping means you don't just put all your data on one disk and build a mirror. Instead, your data is split across. So you have what's called bit level striping versus block level striping. Bit level would be you can have, you split a byte into 8 bits, and each disk gets one of the bits. And that way you access them in parallel. Why? Because by the time I spend the same amount of time reading all these 8 disks in parallel, I get 8 times the data, right? Because the bits are split across. But that sounds kind of crazy, right? Who would really do that? Yeah, so that's really more for theoretical interest. But that is what allows you to achieve kind of the upper bound on your performance if you really have to do it at that level. But more commonly, you do what's called block level striping. And the block, of course, here means more like a sector, or more like, or in the OS terminology, block here really means the basic unit of transfer, right? Or it could be like a page granularity. So you would say, I have a disk block or a sector. Instead of going on the same disk, well, now you go to a different disk, go to another disk, so that when you access them, they get read in parallel. Okay, ideally that's the case. But guess what? That may or may not happen, right? Because you do have, remember, the seek time and rotational latency. They're not always going to be having the same luck. Rotating right under that sector you want, or they may have to seek to a different place, right? And so there are ways to, that works only if you even now, or you keep them, their access time, latency the same. But that could be different if you have different defects on the disk, and you have to skip bad sectors and all that. Okay, and so, but anyway, RAID has many different variations, and I don't expect you to remember all these numbers. These numbers are a little cryptic. They don't really mean much, but I mean, you do need to be aware of their differences, okay? So there's something called RAID 0, and what RAID 0 means is all you're doing is doing striping. And striping means you do need a minimum of 2 disks, or else, that's by definition of striping. You do need to split your data across disks, right? So that means you have to have at least 2, sometimes more, to get that parallelism. Now, RAID 1 is to do mirroring, sometimes called shadowing. So that is to have a redundancy. And so that means it's the same data, you write multiple copies, 1 copy onto each disk. Usually 2 disks is fine because you've seen the mean time to data loss, right? 2, if you work out the average, it's 57,000 years. And if you do 3, that starts to get really expensive. Okay. And there's something called RAID 1 plus 0 and RAID 0 plus 1. So 1 plus 0 means stripe mirror, 0 plus 1 means mirror stripes. Like, what? What are those? Okay, again, I don't expect you to memorize that 0 plus 1 means this, 1 plus 0 means that, but you just have to be aware of the kinds of things they can do. So stripe mirror, what does that mean? That means first you do striping. Okay, so that means you split data across. But then for each split part, you make another mirror of it. Really? Why would you do that? It's because that way you allow the different parts of the data to be mirrored. And the other way, mirror stripe, means you have one stripe system, which is essentially RAID 0, right? And so then you make an entire copy of that stripe system, entire mirror of that stripe system. Okay, and so the trade-off there would be, well, in terms of RAID 1 plus 0, you have much better mean time to failure, right? Because then each bit now has like 57,000 average time to data loss, that is. And 0 plus 1, the issue there is you have one stripe system that's mirrored over the other, but you have to think of in terms of this whole stripe system being able to have one long enough mean time to data loss. But then if you take 4 of them, the problem is these independent ones are then you're limited by the worst case of the 4 in one stripe system, and also the worst case on the other stripe system. So that means the chances of them having a real the mean time to data loss is limited by the worst case in each of the 2 stripe systems. So that's why 1 plus 0, even though that sounds a little bit fine-grained, that turns out to be the better choice. And it may be a little harder to build a controller because it actually has to be working at possibly splitting a byte across and then putting them together. So the RAID 1 plus 0, in terms of storage use, that's actually a better deal because the same amount of storage as your RAID 0 plus 1, but it's a little harder to build a controller for it, but in the end it achieves better reliability. Okay, so that's another way to view 0 plus 1 versus 1 plus 0. So 0 plus 1, basically you do the mirror of this the stripe system, and then the 1 plus 0, so you stripe, but then every stripe is mirrored. Okay. Now there's additional RAID levels, RAID 2, RAID 3, 4, 5, 6, 7, all those. So these are trying to make a little bit more frugal use of the disk. So instead of mirroring, they say, well, you don't really need to make exact copy, do you? I mean, you just store these error correctable code. And that way, most likely you use something that's Hamming code, but there are others. And that way, the error correctable code can correct up to a number of bits of error, detect a number of bits of errors, because you're hoping that you wouldn't get simultaneous failure. I mean, the chances of that happening is really, really low. So now, RAID 2 uses what's called memory-style error correcting or error correctable code, and then so I can talk a little bit about Hamming code in a little bit if you haven't seen it. And so Hamming code would be these additional bits you use for both checking and correcting. So you don't need to use as many bits as you have your data bits. And what it does is it computes these based on your multiple of your data bits. And these Hamming codes get saved onto these on a separate disk. And that way, in case of any failure, you could not only detect but also correct and recover from the remaining bits that are not wrong. Now, RAID 2 is an okay idea, except guess what? Most of the work is not done by OS or software. It's done in hardware, okay? Including the ECC error correctable code. Hardware handles it. I mean, on every access it checks. It's very simple computation. Hardware does it. For software to do this, lots of bit manipulation and or shift and all that. It's not practical. So RAID 2 is really more of theoretical interest. RAID 3 would be bit interleaving parity. So that is instead of using your own copy of error correctable code in software and save onto your disk, what it does is it just saves the parity, right? Remember, even parity or odd parity. So it's a bit such that if you count the number of bits in the data and the data bit, for even parity, it should come out to be an odd number. Oh no, even parity would mean the count should always be an even number. Odd parity should be should be an odd number. And so the reason here is the parity should be enough. Because disks have their own error correctable code, and disks actually know which one failed. And so in order to reconstruct, actually that parity bit is all you need, okay? And that's where the error correctable code may be able to help you up to a certain limit, but if it can't, then you rely on your separate parity bit to help you with the data reconstruction. So here's what Hamming 7.4 code looks like. So Hamming 7 code, it means 7 bit would be the total. That means 4 bits of data, 3 bits of Hamming code. And these are 3 parity bits, but then they are not just any parity bits. So so P1, P2, P3 are the parity bits of Hamming code. P1 would be parity for D1, D2, D4. P2 would be for D1, D3, D4. P3 for D2, D3, D4. Okay, that way you get everybody covered, and so it can detect and correct a single bit error. Okay, and so that's better than full mirroring, because with full mirroring, 4 bits, you need another 4 bits of mirror, right? Here, you save 1 bit, so you can detect and correct. Okay, as long as the number of bits wrong is 1 bit. And most likely, that's the case, okay? So detect and correct. But if you have multiple bits, it may be able to detect, but you can't correct. All right, so that's the concept of parity and Hamming code. And RAID levels keep going up, 4, 5, 6. And so now RAID 4 will be block interleaving and then parity on separate disk. So it's like RAID 3, but instead of bit level, it's block level. So more practical. RAID 5 would be block interleaved, but then with the parity distributed on disks rather than on a separate disk. Okay, so that way it may be helpful. And then RAID 6 will be using a different kind of redundancy, P plus Q. It uses more bits to be able to recover from multi-disk failure, but I'm not going to tell you about the details of this, because that's really outside the scope of what an OS does. Pretty much all of this is done in the controller now. So the different levels, RAID 0 plus 1 or RAID 1 plus 0, so that's the trade-off between performance and reliability. And then both use mirroring, so that means it uses more space. Now, RAID levels 4, 5, 6 are attempting to save the redundancy space, right? So that way, either using as little as just 1 parity disk, or you spread the parity over, or you use some additional code. And so that way, you save the redundancy space. And now, RAID within the storage array can still fail, right? And so what RAID controllers do, trying to be smart and taking more automation, is they would do automatic replication when it detects some data is failing, and you can bring a hot spare online on its own, or you could try to do some type of checking, so something a little smarter in case of mirroring. So if it's already the same, you may limit the updates or mirroring action to only what's changed, rather than recopying the entire thing. Hot spare disks would be one that is not one of the ones in use, but then it's a good one, new, and then gets brought online when one of the disks fail, and so it replaces. It kind of stands in for the other one, and the other one just gets disabled, and then so somebody has to manually remove it and then put in another hot spare in that case. Okay, so now with disk management, there's a few other features. So snapshot would be like taking a snapshot of the file system before you're about to make some changes or make a set of changes. And so there are some file systems that actually support this. And replication would be to automatically copy and propagate the writes between separate, not only disks, but also different sites. So that means that's to increase diversity of your storage, right? Because locally, if you have a power surge, that affects probably all of your disks. Whereas if you then send over the network backup someplace else, then that reduces your chance of having the same trigger to damage all these. So I remember my PhD advisor, he was from Italy, and then when he was doing his PhD at Berkeley, he always sent a copy to Italy just so that he has a backup of his thesis at a totally different site. And that's a way to, to ensure you if one disaster happens in one place, chances are it's not going to happen in this other place, like big earthquake or things blowing up. And it could be done synchronously or asynchronously, right? But synchronous would be waiting for that replication to complete, but that's going to mean much longer wait time. Hot spare disk, as mentioned, is pretty common, certainly used in RAID as well, and it can be automated or automatically brought online, so that decreases your mean time to repair, and therefore it decreases your mean time to failure, data loss. Okay. And now, of course, this OS does get involved at some level. In terms of data corruption of detection, OS really sees this more at the level of file systems. Okay, so yeah, it does rely on the disk hardware controller to report any failure. That's the job of the hardware controller. But OS does have to handle. So what happens when something fails? Then it needs to make attempts to avoid certain parts of the disk, or attempt to make copies, recover, and so forth. Okay, so now RAID mainly handles disk failures, but file systems would handle like the structure or the way things are linked. And so there is still a checksum in there that could be added by software, in this case operating system. Why? Because it does need to ensure that in case the disk fails, and you don't just throw your hands up and say, no, there's nothing I can do. It always does have to do a little bit more beyond. So this is assuming the disk has done its best, but still couldn't do anything. Then the OS does keep these additional structures at software defined. And then the checksum would then keep a pointer to objects. So that's how a lot of times when you do a disk check, it takes a while, but it's actually checking not only the data structures, but also are they consistent, self-consistent, so with the checksum and all that. And then if the object is the right one, what is changed, and so it can detect and correct these data and metadata. Metadata would be to say, like your directory structure, right, and how big the file is, and the way these files are linked. And so when we cover the file system chapter, you'll see that. And also, the OS has to do allocation, and also there's the volumes and partitions, and right. So that's what that's what OS has to do, and it needs to depend on disk a lot to report back and to store important information. But how much can it trust the disk? That's why the OS has to do these extra things and be able to mount or remove these volumes and partitions. So that's just a little bit more about what the ZFS checksum and metadata. So in addition to just the different fields in these metadata blocks, so that your process control block, or in fact more into the disk, right? Anything you save to disk, OS would add additional checksum in there, just so that it trusts this to a certain level, but it has to be sure for itself. That's why these things get added. Okay, and then OS can also combine the different volumes or different disks into one uniform structure. So the user only thinks in terms of one file system, one file, but it could actually be spread across. That's not always done with all OSs. A lot of OSs expose you to the actual partitioning. So you may have partitioned your disk into like 3 different partitions, and your OS probably shows them up as 3. But certain file system like ZFS can pull the storage, so you can keep adding disks, and it still looks like the same partition to you. Okay, it builds that abstraction. Okay, so that's what I have for this chapter, and look for some review questions a little bit later. Next, what I want to talk about is your programming project. So I hope you guys have been making progress, and now, so since the midterm, you have a lot less work to do, and I was hoping that you would spend some time on your programming checkpoint. And it is important because I do think that this is the kind of thing you really have to get your hands on and work on in order to really understand some things. You could read about semaphores and threads all you want, but you don't internalize until you actually get something like this working and know exactly why. Okay, and so now there are a total of 5 project checkpoints, and now this 4th one it's been posted. I think we put it online a little while ago, but in case you haven't seen it, so there are a total of 5 checkpoints, and so just to remind you that if you really need to get one checkpoint completely working before your next one will work, and for grading, we'll only grade you on the last one you can successfully complete, and everything before we don't need to grade because by definition they have to be working, so your points get added up that way. Okay, so now so you remember checkpoint 1 was just cooperative multi-threading. You should have all gotten that working by now. Preemptive multi-threading may take a little while. That's checkpoint 2. But once you realize that it's just the timer interrupt instead of your yield, everything else is pretty much the same. So it's really not as hard. So getting the cooperative multi-threading to work, that is probably what takes the most work. But then once that works, the preemptive one is actually a lot simpler than you might realize. And once you get that working, wow, okay, you'll feel quite good about that. And checkpoint 3, that's on semaphore, and that involves a little bit low-level trick, right? Because we don't want to put additional pressure on the stack by making another function call, pushing another thing on there. So we do it in inline assembly, but that's actually not a bad thing because then you get to know exactly what's going on. But if you can get it working with function call, okay, more power to you. But I don't think that's the best way to do it. Inline assembly, that's where you get to write a little bit of assembly code. Nothing all that difficult, but I think that's the fun part. And once you get the semaphore part working, now that's a very, very basic semaphore, okay, right? And run a few test cases. Then checkpoint 4 is on just more of these tests. So this is to test preemptive multi-threading and semaphore code, and using this bounded buffer example. But in this case, it's also there's it's doing 2 producers, 1 consumer type. Okay, and so that means the 2 producers are competing against each other and then writing. Okay, and this is where it will be potentially counterintuitive. You might think, well, we're just doing round-robin scheduling, right? Everybody gets a turn to do, everybody gets to execute. But then, if you start running the example, you will notice something. Even it's something that's counterintuitive. That is, one thread always gets to run, the other thread never gets to run, or that never gets to make progress, even though you're doing round robin. Like, how can that be? Well, yes, so that's a funny situation, and if you can figure it out, great, even better. Okay, but anyway, so now so this is assuming you've already gotten your semaphore part working. Okay, and then to do the preemption, or you can do test preempt from the previous checkpoint. And so instead of 1 producer, you make producer 1, producer 2. That way you don't have to try to write reentrant code. That's fine. I mean, if you want to keep it to the single copy of producer 1, producer 2, and then make your code reentrant, well, more power to you. But this is probably good enough for now. And producer 1 just outputs letters A to Z, repeats forever. Producer 2 is 0 to 9. So that way, you, based on the output, you know which thread gave you that value, right? Consumer is the same, and of course, they rely on the semaphore. So this way, whether you use a separate thread for your package or you reuse main, that either one is fine. Okay, so you should have enough threads in this case. So yeah, and this is one place where you do get a fairness issue. So if you use round robin, now you will see output from only 1 thread, which one depends on the order in which you spawn them. And then if you switch the order, you see the output from the other one. You say, really, why? I'm doing round robin, this guy's supposed to execute, right? But no, it doesn't. And so what happens? And I think this one is very interesting. And I shouldn't give away the answer at this point, but you should really think about it. And first, try writing the code, get it to work, and yes, that's great. That it works. Then think about why it is a case. Okay. And right, so it's like I think we give you pretty much all the code, and this one shouldn't be that difficult to do because it's really additional tests for your checkpoint 3. Okay, so make sure you get to your checkpoint 3, get it working very soon. And then this is a way to stress test it, right? And so then, and at some point, if you try it and get stuck with something, then ask one of us to help you. And I can even do a debugging session in class just to show you what's happening. Okay, so yeah. Yeah.
How do you say that we have 5 checkpoints?
Yes.
This is the 4th one.
4th one, yes.
What's about the 5th one?
The 5th one we'll post shortly, and so
about what?
It is. Well, if you really want to know, remember that parking lot example?
Yeah.
Yes. Yeah. Let's do a stripped down version of the parking lot example. And so that way it uses a few more things. So yeah, that's what it is.
They get some idea about the checkpoint number 3.
Uh-huh.
The checkpoint number 2 when we are using frame. Currently we have to save the registers also. We have to, because we have to keep the context of each thread. So if time that we are jumping to another thread, we have to save not only the A, B, and the P, PSW, we have to also store the registers. But I was thinking that in that case, why we will need to use bound registers? Can we stack all of those values also in the stack memory for each thread and use only one bank? Can we make these kind of things, different layout distribution in our project, or we have to follow the distribution of
well, okay. If you can get it working and explain, great, more power to you. I tried a number of different things, and this is what works for me, and this is what I can explain. But this is by no means the only way to do it, right? So if you can think of another way, I mean, even I can think of maybe alternative ways. So, but you do have to realize which stack are you using. You do need separate stacks for sure.
Yeah, sure.
Right.
Yeah, sure. That would be the meaning of different threads.
Right.
Because we have to use
That's right.
different stacks.
Right.
Right. Because my current solution for the checkpoint number 2 is using only one bank of registers, R2, R0 to R7, pushing in the same stack, in the stack of the current thread. So it's working on that, but it's not following your layout distribution.
Okay.
So I was wondering that if that is
Now, which registers are you saving? Are you saving all of them?
all of them.
No, you're gonna run out of registers or run out of stack space very quickly.
But
Yeah.
the thing is like because I'm using I'm stacking all of the registers in my stack. I don't need to use 4 banks, so my stack is starting on 0, 7.
Correct. You will, but do you have any space for heap? Any global variable?
I have a heap, and my heap is enough. I guess it's working at least for the.
Okay.
But the thing is like I totally design a new layout memory, and I was wondering, oh, maybe that is totally wrong because I'm not following your layout memory. So I was thinking that it's allowed it to.
Okay, as long as you can get it working, I'll allow it.
Okay, because in that
um,
point for the checkpoint number 3,
Yeah.
I'm using I'm using the same semaphore that you are proposing,
Mhm.
the bounded buffer,
Yeah.
but I'm already introduced another semaphore. It's okay if I change these kind of things. If I introduce another variable in the standard semaphore of the bound buffer.
Yeah, it's just that you'll be giving the TAs a hard time to help you.
That's why that's my question, because I changed some things that at least for me is working, but
Sure.
I don't know.
More power to you, yeah.
No, the thing is like maybe I am putting too much variables, and it's making more complicated the system, and that's not gonna be counted as a good answer of the solution of the problem. So that's really my question. My question is, should I stick or should I try to follow your layout, or it's okay if I come up with a new layout
That's kind of
as long as it's
my
working?
well. There's a reason I put up this the write-up is because I worked through it myself. It works. I can explain to you, and if you have much better chance getting it working this way, right? So that's what I would recommend. And if you already went through and got your part working, I think it'll be easy for you to switch to this layout if you choose to. But yeah, I think it's admirable that you're trying things a different way. I think that I like to encourage that.
The thing is what I tried different ways, because at the beginning when I was trying to do in the layout that we have it, I got really huge problems that I couldn't solve the problem following the layout that you give us. Only for the checkpoint number 1, I'm following the same layout and it works. But for the other one, I tried to do some change, and in some cases it's failing. So that's why I come up with another ideas.
Well, I suggest you either ask TA or at some point, if they can help you, you can ask me. We could figure it out. Yeah.